Started. Thank you all so much for joining us for stainless steel selection to avoid corrosion. This is brought to you by the AIA provider, the International Molybdenum Association, IMOA, and co-sponsored by the Nickel Institute. Both are trade associations who sponsor research and provide independent technical information related to molybdenum and nickel-containing materials. If you like to learn a little bit more, I will be placing links to both associations' websites in the chat later on in the webinar. Just a couple of housekeeping items. Please save your questions for a Q&A session at the end of the webinar. And also, if you are seeking AIA continuing education credit or certificate of completion, please see join information in the chat if you did not pre-register. Okay, now let's meet our speaker, Catherine Hauska. She is an internationally renowned expert in architectural and structural metals who actively participates in multiple standards committees, including AISC 370 and 313. She also chairs the ASTM E60 General Sustainability Committee. She's also authored over 200 publications, including contributions to AISC's Design Guide 27. I'm very pleased to welcome Catherine, who will now begin our presentation. Thank you very much, Catherine.
Thank you, Carly. It's a pleasure to see everyone. Good morning, good afternoon, good evening, wherever you happen to be on the planet. I did note that we seem to have people attending from around the globe. So it's wonderful to have you. I will note in advance, if apologies if my dogs make noise. My headphones chose not to work. So we're going to talk about avoiding corrosion with stainless steel. I'm primarily going to be looking at this from an aesthetic point of view, but certainly some of these forms of corrosion could cause structural failure as well. With that, I'm going to dive in and mention first that these are copyrighted materials. You can't use anything from this presentation without permission. So please contact us if you really need a locked PDF for your information. Everyone who goes through the alternative sign-in process, which is shared in the chat, will get AIA credit or a certificate of completion, and some of the structural engineers, depending on the state, may be able to use this for credit. And I wanted to first, on a high level, review the learning objectives. We're going to cover at a pretty high level the fundamentals of the causes for exterior environmental corrosion from an aesthetic or structural, and to avoid aesthetic or structural failures. We'll learn about evaluating the corrosiveness of environments to select the appropriate stainless steel and how different aspects of your specification, like finish and design detailing, can affect the performance of that stainless steel. The finish you apply is just as important as the alloy that you select. I'm going to be introducing you to a scoring system that I developed for the International Molybdenum Association with input from other corrosion specialists around the world. It is geared toward aesthetic applications where any staining is a potential failure. But I will also comment on situations that could cause a structural failure. So I'm going to talk about resources as I go through. Carly will be sharing links so that you can find some of these as well. You go to the IMOA website, there is a selection system. And there, in addition to the page that I am showing that gives the introduction to it, there are case studies, there are specific pages on avoiding galvanic corrosion, coastal salt versus de-icing salt, and other things that should be considered. For example, if you're doing a green roof or green walls and you're using stainless steel, you want to make sure that that stainless steel is appropriate for a soil environment, because fertilizers, even organic fertilizers, are corrosive. So I'm going to talk a bit about some of the other resources on subsequent pages, including guidelines for corrosion prevention. But I did want to let you know that on our website there is both IMOA's website, but it was developed by both organizations. There is a library that you can download with over 500 publications. I am going to be referencing National Atmospheric Deposition Program data and maps. That's free. You just have to log in, find the right page, and you can get data on what might be corrosive in your location. There are similar data sources in some other parts of the world. And of course, there's site corrosion-specific research, which a metallurgist who focuses on atmospheric corrosion would probably have access to. So today's presentation will primarily be focused on information that is in these two brochures and on IMOA's website. The scoring system, which stainless steel should be specified, is a few pages long, and it is a scoring system. It provides some brief guidance on things to consider. Guidelines for corrosion prevention is a Nickel Institute brochure that I think I wrote probably 15 or so, maybe 20 years ago. It was updated a few years ago with a bit of information. It is a much more detailed brochure with a lot more examples to help you avoid some of these problems. And it has other fundamental design advice. So where do we start? All materials will deteriorate if they are exposed to something that causes, well, corrosion or deterioration. Pollution is certainly a factor. The exposure to it varies dramatically depending on the part of the world you're in. That image is one that I took in Beijing on a particularly smoggy day. If dust or debris will accumulate on a surface, that can cause crevices. And that can be a place where corrosion initiates if it's not cleaned off. It could be leaves as well, and not just the type of dust that you might see accumulate in some parts of the world. Any form of salt, coastal, or deicing will accelerate the deterioration of materials. Weather conditions play a big role. Their role varies with a specific material, and I'm going to focus on stainless steel, but it is important to assess your site and what is expected, both in terms of weather, but also whether maintenance cleaning will be done, how frequently, and what will actually be cleaned or not. Design makes a big difference. If you've left crevices that are not sealed, or you pick a very rough finish, then that will change the equation. So, the U.S. government has occasionally done studies looking at the annual cost of metallic corrosion if the wrong metal is selected. And I should note that the construction number, which is substantial at $50 billion a year for the direct cost, another $63 billion a year for the indirect cost, does not include infrastructure or industrial buildings. So for those who are architects or perhaps facade engineers, anyone that is working on buildings, that's the annual cost of selecting the wrong metal for a building. These piers in Progreso, Mexico are a wonderful example of the importance of selecting the right material for durability. The functional pier was completed in 1941. It's still in use. It's the longest pier in the world. And that was the first large application for stainless steel rebar. It's been thoroughly studied for those who have an interest. It's just fine. That non-functional pier was built 30 years after the stainless steel reinforced pier, and it was non-functional within that period, within 30 years. And, that was carbon steel black bar. Now, yes, you could potentially coat it, but there are a lot of states and provinces in North America that have banned coated rebar. So what's the difference between stainless steel and carbon steel? How does it work? Well, stainless steels are iron-based. They contain at least 10.5% chromium and are low carbon. Carbon steels have, well, more carbon and less chromium. They are also iron-based. Note the name is stainless, not stain-free, unless you select an alloy that really will remain stain-free in your environment without maintenance. It's really a matter of what is likely to happen and what is needed. The family of stainless steels and then alloy selection within it are critical. Corrosion resistance in stainless steel is obtained through chromium, molybdenum, and nitrogen additions. Nickel primarily helps with formability and weldability. There are specific applications where it also helps with corrosion resistance. But the main advantage in the types of applications that most of our listeners will be working on is that formability and weldability. When stainless steel is clean and exposed to oxygen, it will form a thin passive film. It's similar to the passive film that you might be familiar with on aluminum, for instance. And as long as that stainless steel is corrosion resistant enough for the service environment, then it will remain free of corrosion. But it is very important to select the alloy. In comparison, carbon steel forms rust on the surface, a thick uniform layer. When stainless steel starts to corrode, we get little pits on the surface. I've cleaned the sample to clean away the staining that was on the surface so you could see what that looks like. In comparison, carbon steel has uniform corrosion over the surface and a layered appearance. It's not removed, that layered area can actually accumulate more of what's corrosive in the surface and moisture and accelerate the corrosion process. So, some basic rules to avoid problems. The three families of stainless steel that I'm going to mention today, which are most commonly used, are austenitic, duplex, and ferritic families. The differences between them are their microstructures, but there are also differences in strength and their ability to absorb energy. They're also, and additionally, some of these stainless steels, like the duplexes, are far more, more resistant to chloride stress corrosion, cracking, and crevice corrosion. So if you know that that's a potential issue and you can't avoid it, then you might want to consider a duplex over an austenitic. The austenitics are more formable and very easily weldable. If there was a problem with a weld, it's a good chance you could re-weld without it being an issue. It's more forgiving. They also have the most finish options. So there are reasons why austenitics have been so popular in architectural applications around the world. You should never simply say stainless steel in your specifications. That's not enough. That would permit those bidding on the project to use the cheapest stainless steel that they can buy, which might not be corrosion resistant enough or have the other characteristics that you need for your application. Also, please don't just use the common name like 304 and 316. For the purpose of this presentation, I'm going to be using them because it's easier for most to understand. Please use the UNS number. That is within, if you look at the ASTM standards, there is a column that lists the UNS number, and if there is a common name, it will list it beside it. If you read the ASTM standards specification requirements, you have to use the UNS number. Additionally, when you specify the finish, please don't use vague descriptions. Number 4 is a vague description. If you really have to have an aesthetic application and you have to have matching, you need to quantify the finish, the surface roughness, the gloss, color, unless you're having the surface electrochemically covered or applying a PVD color, but it correlates with the surface roughness when you're talking about a material, a stainless steel that does not have color applied. So I'm showing a range of stainless steels on this graph. The least corrosion resistant have the lowest bar. Everything in blue is a ferritic. Everything in orange and austenitic. The duplexes are green. This shows that you can get a wide range of levels of corrosion resistance in any alloy family. The 304 and 316 that are most commonly used in architecture and other applications are at the low end of the scale. If you have a more corrosive location, increasingly 2205 is commonly being used, and you can see it's in the middle. You can calculate what we call a pitting resistance equivalent number, PREN, based on the chemistry of the stainless steel. This gives you a relative ranking of the stainless steels. It is useful for understanding the relative corrosion resistance, but it's also very important to understand that those numbers may not tell you which alloy would be better for a specific environment. So you have to go a step further, but if you're trying to explain the difference in overall corrosion resistance between, let's say, 316 and 2205, it's a pretty handy tool. So when you see L, like 304L, 306L in a common name, that means low carbon. That is only needed when you are welding the stainless steel to avoid sensitization of the weld. That will give you a band of corrosion on either side of the weld if it were to happen. There is no price premium for low carbon stainless steel in much of the world, but I have seen it in Asia occasionally. So it is something to consider. If you're not doing any welding, then you may not need to specify low carbon. Well, in Europe and the Americas, generally you have dual certification of 304, 304L, 316, 316L. This is a map from the U.S. National Atmospheric Deposition Program. We have ongoing data collection in the United States. It does usually take a few years for them to compile this into a map, but you can go to any of the test sites and see the data. There's a similar mapping program in Europe. There's been mapping done in Australia and New Zealand, South South Africa, India. So there are maps around the world intended to help you select the right stainless steel. In this case, I am looking at the total chloride salts being deposited. And so these are both the wet and dry salts. The U.S. is one of the few places that collects both data and where you can see a combined chart. Often it is just the dry salt deposition. You can see that dark orange area spreads quite far inland in much of the U.S. Any area that is dark orange is most definitely a coastal zone. Now, that area varies from year to year. So it would be important to look at a series of years worth of maps. But 60% of the U.S. population lives in a coastal zone where there will be some salt. And that's true around the globe. Generally, you wouldn't want to use 304 in exterior application in a coastal zone, unless it's going to be cleaned frequently, and it's an area with heavy rain, and it will benefit from rain washing. The closer you get to the coast, the bigger the potential issue. De-icing salts can travel much further from roadways than most people realize. This study that I'm showing was done outside of Chicago on the Argonne National Lab property in conjunction with the National Atmospheric Deposition Program and Illinois DOT. They documented over a 5-year period how far salts were being carried from the roadway, and they were mainly carried downwind, as you'd expect, up to 1.2 miles for the dry salt particles. The splash zone was 49 feet. They did look at downtown Chicago and found that there was a salt haze around the city at quite elevated levels for days after a snow or icing event. The highest level that I'm aware of that a consultant has documented de-icing salt concentrations on a building in Chicago is the 59th floor. I found that it varies from city to city, and that it depends on where it is in the city. If you have tall buildings one after the other, and you have a big boulevard that's lined up with the wind direction, they can go very high in a building. But you could go around to the side of the building on a quiet street, and it might only be up to the first floor. I have personally documented de-icing salt that traveled 2 miles from a roadway. It was in a rural area. The bottom of the building had 0 salt on it, but the top, which was in direct line with the highway, and wind was being channeled up a valley, had de-icing salt on the surface that had caused deterioration of a colored stainless steel finish. So it is critical to assess the environment. You should also be thinking about what might happen with sea or brackish water immersion. Separate from the developments that are being created floating on water, we unfortunately have increasing levels of climate change, which are causing dramatic flooding in some cases. This is a picture of New York after Superstorm Sandy. This immersion in sea and brackish water lasted for days. In the case of the tunnels, transportation tunnels, it was a whole lot longer than that. So you need to consider whether there'll be immersion in salt or brackish water. If it's longer term immersion, then we do have wonderful data to help guide the choice. You'll see in the graph I have here, there is no 304 or 316 in this, despite comments on the internet that 316 is a seawater grade stainless steel. I can assure you that it is not. 2205 and 904L are the lowest alloys we show. And for long-term immersion in sea or brackish water, they are not a permanent solution. It really depends on the chloride level and other factors. So if you are going to have a project with longer-term immersion or in sea or brackish water, you really need to be speaking to someone who was an expert on that type of corrosion. These are railings in New York City and in the Canary Islands. I've had the opportunity to give presentations around the world and talk to people who are responsible for maintenance of public railings. No matter where I was, I heard stories of painted carbon steel railings that were painted every year that would structurally fail within 8 to 10 years. It was very consistent everywhere on the planet, wherever salt spray was going to be hitting those railings, even though a lot of maintenance had been done. These railings in New York along Hudson River Park are a form of 316. There are areas where there is staining on the surface, where there is more splashing, but it's superficial. These Canary Islands railings, as you can see with the rocks below, are basically a natural salt spray test. A 316 demonstration railing was put up. Within a few weeks, it had significant staining. They thought that they'd gotten the wrong alloy. The stainless steel producer sent somebody to take a look because this was going to be a large project. And they said, yeah, wrong. That alloy is never going to hold up in this essentially a salt spray test. They ended up using duplex 2205 with a smooth mill finish, and this is what it looked like 30 years later. No problems. It's all a matter of the right alloy. There is a lot of research data available to those corrosion specialists like myself who collect this. There was one study done by Outokumpu in the Middle East, and they kindly shared the data with me. I converted it into something that probably means more to most who are working on buildings. I assumed a roof, and I used the thickness right out of the SMACNA architectural sheet metal manual and put in the corrosion rate and calculated the time to perforation. This is based on the average corrosion rate, so perforation could well occur before that. 2205, depending on the finish, did have some very light staining as they extended the testing, but it wasn't measurable. So the time to perforation would be over 50 years. In comparison, everything else corroded at a very rapid rate, with aluminum having the next best time to perforation at 16 years. So there is data from South African data, and you can see this here. I'm comparing more materials. If you look at Durban Bay and Walvis Bay, which are the most aggressive marine environments, you can see 316 and 304 versus weathering steel and mild steel. And there's a huge difference in corrosion rate in a more aggressive location. So there is data to assist with these decisions. I live in Pittsburgh, Pennsylvania. This is the equivalent of the second floor of 3 different buildings. One was 430, another 304, and the final one was 316. And it had been about 3 years since any of these had been cleaned. Being local, I'm often asked for cleaning advice. And that difference in level of corrosion is directly related to the alloy selection. They all had a very fine wet polished number 4 finish. So it wasn't a finish difference. With a 304, that's superficial. With a wet cloth, it wipes off. It's much like the Inland Steel building in Chicago. First thing in the spring, there's staining on it because it's type 304. There are other examples in older buildings. That 430 has pitting that is visible and will eventually probably perforate. More samples from Curie Beach on the Carolina coast after 57 years of exposure. That is considered a moderate coastal environment, low pollution, not particularly high salt exposure. You can see the difference in appearance over time. From the same location, what used to be a galvalume coating on carbon steel after 48 years. So please look at the data that's out there. Some of that is in Guidelines for Corrosion Prevention, which is one of the brochures that I mentioned to you. There's been quite a lot of research on the relationship between surface roughness and corrosion performance, mainly for industrial applications. I've done some myself for some of the polishing houses. But the general rule of thumb is that if you have a surface roughness of RA 0.5 microns or 20 microinches or less, then you will have a much lower corrosion rate. So those smoother finishes will need less cleaning, they'll accumulate less dirt, salt, whatever is in the environment, and they will perform better. If you really think you need a rougher finish, if you aesthetically have to have abrasive blasting, then the corrosion rate will be a lot higher, and you might need to use a more corrosion-resistant stainless steel to achieve an acceptable aesthetic finish. In another Nickel Institute brochure, Timeless Stainless, I did a survey of finish suppliers in North America and Europe and included that in this table. You can see that a number 4 finish, which is very popular, can be very fine, or it can be rougher. So it could be on either side of the line that I just showed you. If you have an aesthetic application, or one where you really can't tolerate corrosion, it is important to not just say, I want a number 4 finish, but to also define the surface roughness, the maximum or range that you find acceptable. I usually suggest a range if you need to have aesthetic matching. This is an example of crevice corrosion under a bolt on a pavilion in Florida. It was type 316. It was the only area where there was corrosion. There wasn't any sealant under the bolt heads, and there was crevice corrosion. Wherever you have created a tight crevice that where salts and moisture or pollutants can get into that crevice, you will likely have a place where crevice corrosion can occur. Sealing the crevices or avoiding them is ideal. If you're going to use a woven metal screen, like woven stainless steel, sunscreen, or similar, then you need to make sure that the alloy that you've specified has enough resistance to crevice corrosion so that you don't end up with crevice corrosion where every single line crosses. Galvanic corrosion is another very common problem. I've given presentations to architecture firms, multiple firms, where I've been asked to stop when I get to this point because they have had problems with significant problems with galvanic corrosion, mainly when they've used aluminum to hold stainless steel or copper panels in place. So they've got, aluminum structural sections that have corroded away. So let's talk about the basics. First of all, there needs to be a difference in the corrosion. You have to have dissimilar metals and a difference in corrosion potential. There has to be direct metal-to-metal contact, and there has to be moisture on a regular basis. So it's not likely to be a problem inside a climate-controlled building, unless you have a bigger problem like a leaky roof. Ideally, you want to, avoid those combinations, but that's not always practical. But what you can do is use a non-conducting barrier. There are a variety of different materials, polymers that are used between metals to seal them. The appropriate choice will really depend on likely movement, temperature, and a whole variety of other factors. You can paint joints that are welded to each other. So you paint, you have stainless steel welded to carbon steel, paint the joint. Paint at least 2 inches out from the joint. And then someone needs to inspect it to make sure that you maintain a paint barrier to prevent galvanic corrosion. I'm showing a picture of a cast aluminum that was painted, but the arm above it moved, so the paint wasn't going to last. And you can see there's galvanic corrosion of the aluminum under the stainless steel piece. The bottom picture was taken at a very wealthy person's private residence. These stainless steel structural sections held the house several floors off the ground because of storm surge concerns, but the bolts were galvanized steel, and they are corroding at a highly accelerated rate. Type 304 is great for rural and suburban areas with low pollution levels and where you don't have salt or there's not much salt exposure. The Gateway Arch has type 304, it's structural on the exterior. It is in a park setting. There is some corrosion on it, but not much. It is, doesn't get direct salt exposure from de-icing salt other than right at the base, and they've been changing what they're doing there. Most of the discoloration on it is actually from industrial pollutants when St. Louis was, a much more industrial city. But if you have a smooth finish and you have regular cleaning, sometimes you can get away with 304. But both of those have to occur. 316 is the better choice if you have a bit more pollution and you have low to moderate levels of salt exposure. This is a museum with a 316 exterior, and I took that picture from a highway bridge. The panel close-up was the panel closest to the roadway, and right by the crevices, because this was 316, you can see a little bit of discoloration, not much. It would have been easily cleaned off, but otherwise it's held up well, other than some dirt streaking. This is an example of the type of application where you really need to use a more corrosion-resistant stainless steel. These are type 316 railings around the Hong Kong Convention Center. They have a really rough finish. The bolt heads have a smoother finish, and that's why they're not corroding. But, spray and splashing of salt water is going to happen every day. Ultimately, there was a decision made to clean these very frequently, I think on a weekly basis, to get the salt off, after they'd removed the staining. But that's not practical for many parts of the world. In comparison, the Franklin Delano Roosevelt Memorial in New York City, was designed for a 100-year storm event. I was on the team that worked on this, and I was told it had to survive a 100-year storm surge, which would mean that the railings and the bits of stainless steel holding together those blocks of stone could be immersed for days in salt water, and they didn't want to have to refinish. So we went with 2205. They also wanted a quite dull, rough finish too, so that was another factor in the 2205 selection. The grand opening was weeks before Superstorm Sandy came through. Yes, everything was immersed for days. There were trees all over the place. There was zero corrosion of the 2205. So it met that requirement. So IMOA has developed a site and design evaluation system. This was work I did for them perhaps 20 years ago. We've continued to update it. It is really intended for aesthetic applications. The score that you get determines which alloy is most appropriate, and it guides you to really corrosion-resistant levels. If there is pollution, then you give it a score. So in a rural area, you're generally at 0. In the United States or Europe, you're not likely to be above a low or moderate level of pollution in an urban setting. In developing parts of the world with very high pollution levels, you could be at a 3 or a 4. And this is why. You can see a comparison of the particulate levels and sulfur dioxide levels in different cities in different parts of the world. This is an acid rain map that came out for China. I'm not sure of the accuracy, because there are certainly areas in northern China that we know are a lot of industrial pollution, but they did admit that the acidity of some rainfall was less than 4. In comparison, in the United States, we really don't have an acid rain problem any longer. This is starting to change in the Pacific Northwest with pollution that's coming from Asia. So with coastal or deicing salts, the distance from the water will determine how high that salt concentration is likely to be on surfaces. Part of also suggesting that you look at the National Atmospheric Deposition data is that, well, I've provided general guidelines here. There are locations that are different, where higher levels of salt travel further inland. Generally, it's the first, the areas with salt spray in the first 100 feet that have the highest levels. And then once you get past that, the salt levels start to drop considerably. But there are exceptions, which is why if you can have access to data, and we certainly do in the United States, I suggest you look at it. And that's the map I showed you previously. De-icing salt is a bit harder to gauge in terms of how far it might travel. It really depends on the conditions. If you've created a canyon that happens to be lined up with a primary wind direction, how much salt is used. Generally, the highest salt exposure is on the first 3 floors. Sometimes it's just a few feet. It really depends on the specific setting. So evaluating the site is important. If you talk to the cleaning contractors for a given city, they generally will know how high salt goes on buildings in an area. And I should note that 70% of the United States has some de-icing. Again, this is showing you again this map with data from the area around Chicago. So there is some data out there, not as much as we'd like. I'm mentioning salts because the type of salt matters. We've switched to using a lot more calcium and magnesium chloride for deicing. Those are in sea salt, but in a much lower concentration than sodium chloride. So if you have an application where deicing salt is being used on the adjoining roadway and they're mainly using calcium or magnesium chloride, and you can look at public records to determine this, as soon as you are above freezing and you have at least 45 to 50% humidity, those salts are being active and they're actively corrosive. When we used to use just sodium chloride, rock salt, you had more time before you had a corrosion issue. You had to get up to 50 degrees and 76% humidity. So a lot of spring rain washed it away before you had active corrosion on buildings. So we have changed our environment. There's a reason why more corrosion is happening. In addition to common de-icing salts, there are other products that are being sold for de-icing, including fertilizer byproducts, which are still corrosive. Calcium magnesium acetate is the safest in terms of your not damaging stainless steel, but also being far less damaging to concrete. Sand, molasses, and there is a state that's used in molasses because they grow a lot on their highways, has the least environmental impact. And the whole world where there's snow and ice is de-icing. Weather patterns make a big difference. If you have a temperate climate with a lot of regular rain, then you get to subtract points. If you have a hot climate where there's low daytime humidity, and if you look at the average, it might be less than 50%, and very little rain, then we have to increase the score by two. And I should note, I'm mainly concerned here with a desert region on the coast, not an inland region. So if you were to look at their daytime versus nighttime humidity, or the average humidity would be very low. If you look at the nighttime humidity, then you might be up at 80%. So the time of wetness, the time when corrosion occurs, is at night. So if you're not looking at those numbers separately, then you can think that you have a situation that's not very corrosive when it actually is. So design considerations. Surface roughness can add a lot of points. I showed you the effect of surface roughness on corrosion. If you've got unsealed crevices, you have to add a point. If you've created horizontal surfaces that are shelves that can accumulate more salt or debris, you have to add a point. There are a number of factors that can make a situation more corrosive. This is an example from Australia. The specification called out a rough finish. The supplier tried to talk them into a smoother finish, asked if they could polish an area, and this corrosion difference is strictly related to the surface roughness. If the whole railing had a finer polish, then it would have not had a corrosion issue. And I just wanted to remind you again that we have provided you with data. Sheltered locations collect a lot more salt, so areas under a building eave or any sheltered area on your building will have a lot more salt accumulation. There have been numerous studies on this around the world. The most extensive was in Japan at various distances from the water, but it's an island nation, everywhere has salt. So the roof had enough rain to have very little salt accumulation, while increasingly sheltered areas under the eave had substantial accumulation. And this was just a reminder about crevice corrosion. Again, look at things like woven stainless steel and be careful about your selection. This is an example of a light fixture where they didn't seal the crevices, and that's where the corrosion was. Maintenance is important. If your owner is willing to do that, the more maintenance that is done, the more points you can subtract. With stainless steel, please, if you can, take advantage of natural rain cleaning. If it's appropriate for the application, power washing works well. Often you can simply clean the stainless steel with whatever you're using on the windows for window cleaning. If you have something adherent, there are a number of things that can be used, but products like Bonami or Barkeeper's Friend can be used sometimes on finishes that aren't near like to take off deposits. Here's an example of one of our case studies, Canary Islands light pole versus railings. And oh, I didn't want to forget the possibility of iron contamination, which has nothing to do with anything else I've shown, but unfortunately happens too frequently. I can't believe they didn't grab my camera and break it when I caught them in the act. But those sparks got into the stainless steel and caused that lovely corrosion. If you get embedded iron on a surface, then there are a couple ASTM standards for removal of that iron. If it's superficial, then A967 would be sufficient. If it's deeply embedded, as it is in this image, then you need to probably grind and pickle. So we have literature for you. There are a number of resources that we have provided, and if you select, you assess the site carefully and pick the right stainless steel, you can have corrosion-free performance. The library that I mentioned is several layers down on the IMOA website. You go there, you have to go to the media center, then to downloads, and then the Building and Construction Stainless Steel Library. There are over 550 PDFs covering these topics. The architecture section, which has information on many different topics, again, is a couple layers down within the IMOA website. You have to go to MOLY uses, molybdenum grade stainless steels, and then architecture, building, and construction. Technical help is readily available, and if you up to an hour of technical experts' time, please go to the Nickel Institute and go to their inquiries section to request help. With that, I'm happy to answer questions.
Catherine, this is Carly speaking. I'm going to go ahead and unmute folks so they can ask questions directly, but we already have one, actually two. Some are coming in on LinkedIn Live and some here. But this first one is from Ken Lee, and he asks, is there any galvanic reaction for different grade stainless steels touching each other? Should be able to see that in the Q&A.
Yes, no, I did just open that up so I could see that question. I can't see the others, but no. I mean, it's not an issue. Well, and I should perhaps, there are some who theorize in some extremely severe industrial applications that maybe, but generally the answer is no, and certainly not in a typical building construction application. It looks like everyone.
Okay. I just have one more question. You could just answer this. It came in through LinkedIn Live. Kunj Gupta asked, what if the water is sweet? Can common stainless steel be used? If you could just please mute yourself. Everyone just make sure you're muted.
Okay, I'm sorry. Could you repeat that, Carly?
I'm sorry. Sorry. Gotta pull it back up. It's having some technical difficulties and it's not displaying me people's comments, but I remember from the top of my head that he asked, what if the water is sweet and can common stainless steel be used in this context?
Okay, you said is sweet?
Yes, that's what the question says. Not sure if Clint can hear us.
So I guess I'm assuming that that's a reference to a specific chemistry. I mean, I'm not sure. I guess I'm not familiar with the term. And I don't know, Gary, are you familiar with the term sweet water?
Not, I mean, I would just say generally it probably means fitty water, something that's been chlorinated and is in good, drinkable condition. Which
in that case, I mean, certainly stainless steel is used for potable water applications. It is especially in areas where you have seismic issues. It's a wonderful choice to avoid damage, from during an earthquake. It's also used for water tanks for that reason too. Although generally at the lower levels of the tank, where if the water's sitting for some time, you use a more corrosion-resistant stainless steel, and there is literature on the Nickel Institute's website about that, I believe, still.
Correct.
About all of those applications, actually. There's some great literature, I think, on both websites about uses in potable water. I see the question, Carly, from a gentleman, someone who says they're a beginner and how can they learn more about grades of stainless steel? And I would suggest there are brochures on austenitic stainless steels, ferritic stainless steels, and duplex stainless steels. While they're fabrication focused, they do provide excellent overviews of the fundamentals, and they can be found on either organization's websites. So I would suggest that as an excellent starting point to learn about each alloy family and the range of corrosion resistance, the different properties and applications, as well as how to fabricate them. Are there any other questions?
Catherine, hi, it's Carly again. I apologize if people are posting any questions or comments on LinkedIn. For whatever reason, I'm seeing the notifications, but when I go to click on them, it is not displaying for some reason. But anyway, as they come in, I will try and relay them. We had a question where someone asked, kindly ask type 316 stainless steel performance against 96% sulfuric acid at various temperatures.
Okay. I would not use 316 with 96% sulfuric acid. There are some good resources where you can look up the performance of different stainless steels in different industrial different industrial exposures. Probably the one that is, I think, most readily available is Outokumpo's. Where you can put in the specific chemistry and concentration and see what stainless steel is, how each stainless steel performs, what the corrosion rate would be. There's certainly books on that topic too. And I know in the Nickel Institute website, there are brochures about specific environments. I'm trying to think of other readily available sites other than Outokumpo's where you can look at a specific chemical and concentration and see what performs. Are you aware of any, Gary?
Well, the one that Outokumpu has is duplicated by what was Sandvik is now Alima, called Alima. They just changed their name for the stainless steel group, so they have that. There's, I mean, for 98% sulfuric acid, it will depend on the temperature, what alloy is suitable. And of course, at the very high temperatures, the 316 is not suitable. At ambient temperature, most people would go with 304 L stainless steel if they know that it will constantly be 98% and no humidity and in the line, so that the acid doesn't dilute.
Thank you. Are there other questions?
Yes, another one coming in from LinkedIn. Is there an LCC calculator app or Excel file available which takes into account maintenance downtime? Great question.
I know there used to be an app, but I don't think it's available any longer. It was originally on I think a CD from the Nickel Institute, but I don't think that was ever updated and made available. Am I wrong, Gary?
No, that's correct. It's.
Yeah.
Go ahead.
Yeah. The problem is too that life cycle assessment is a moving target. And I mention this because governments around the world are focused on low carbon because of climate change are wanting to do this. So there is work being done. In fact, a big conference that ASHRAE is going to be having on this. But there is work being done both at ASTM and at ISO to better define how life cycle assessment should be done, because there are significant variations in how it's being addressed. There is an ASTM E60 standard on how to do whole building life cycle assessment, but I think that's going in a bit different direction than what the questioner had. So it is an area where there is also controversy about how to do a life cycle assessment to begin with.
Also, just a general statement, because a few people have asked if this will be recorded, and the answer is yes, we will have this for recording, and we will share it both on the LinkedIn event, on IMOA and the Nickel Institute's websites, and probably via email as well.
But if there won't be credit for that, just so people are aware, but it will be there as a resource. If you thought that this was helpful and you want to share it with your colleagues, You'll be able to do that.
Yeah. Let's see. Okay, we just have one more question that came in. Your point of view on A1010 stainless steel for bridge applications.
So, all right, there is such variation in the service environments where bridges are used. You know, A1010 is certainly an improvement in terms of corrosion resistance relative to carbon steels or weathering steels. And you know, there are bridges in the U.S. and Canada that have been built from it. It really is a matter of whether or not that specific location is appropriate for that alloy. You probably wouldn't want to use it where there's going to be high levels of de-icing salt use, for instance, and accumulation. I should note that there is an AASHTO committee working on a design guide for duplex 2205 bridges. We're, you know, hopefully by the end of the year, we will have, that will be finished. But, you know, as I pointed out in the presentation, you really have to assess the environment and determine what is appropriate and given your service life expectations. So there isn't, you know, I wouldn't use A1010 for all locations, but there certainly are bridges where it's appropriate, particularly if they're rural, it's hard to get to them. There's not a lot of de-icing salt being dumped on them, but there is, it's a more corrosive location. I don't know, Gary, you've been involved in this too. Did you want to add to that?
No, I think you adequately covered it. There are applications where it would be suitable, and there are applications where it would not be suitable. That's correct.
Catherine, I'm not sure if you're seeing the Q&A chat open here. We have a couple of other questions. There's one from Ahmed asking, isn't chromoly super alloys better for sulfuric acid applications?
You know, as Gary added to my point, it really depends on the temperature. And, you know, the answer is completely different for low temperature versus and elevated temperature. And Gary, you started to discuss that previously. Did you want to add to that?
No, that's correct. As you go up in temperature, you have to change alloys, and at the highest temperature, the 4, 5, or 6% silicon alloys, stainless steel alloys are used. So just say it depends on the temperature, and it depends on the concentration, because the general question, if it's 98%, then it is an oxidizing environment where the steels that have elements that resist oxidizing conditions are better.
Yeah, there really generally aren't simple, you know, answers that cover all conditions. You really have to look at the, you know, all of the factors.
Yeah. And
I should mention that if any of you are structural engineers who are asking those kinds of questions, we did in AISC 370 require you to do an assessment of the environment. And then in the commentary, we list the questions that you should have answered before you talk to a corrosion specialist, so that they can give a more complete answer. I see the question about the corrosion database. I'm not aware of one that can be downloaded. There are books that summarize corrosion databases, separate from, you know, from the stainless steel producers that we've mentioned. There are others that have been printed by different organizations over the years. I think I have an old one on my shelf that came from one of the oil and gas companies. So they are out there, but I'm not aware of one that where it's available for download for the entire database.
And if Catherine, I could just jump in. Oh, sorry. In there, you have to be very careful when you use those corrosion databases, because generally they assume relatively pure chemicals with virtually no impurities in them. Sometimes they'll have one impurity or occasionally two, but in real life you have typically more impurities that will affect the corrosion resistance. So they give you a general idea of what could be used, but then you have to go further beyond that.
Right, absolutely. It could simply give you a red flag, given what you were considering, but the safest thing is to put samples in your process stream and see what happens. Put your candidate alloys in, if that's feasible, or do some other testing with your actual and under your actual conditions.
Hey, Catherine, I'm not sure how much
Yeah.
more time you'd like to dedicate to answering questions, but there have been a lot of fabulous questions. There's probably 5 or 6 more. We'll try to get to as many of them as we can.
Sure. I'm willing to stay on as long as people are still asking questions.
Okay. Right. So let's just go through these first. So Amir asks, will there be more opportunities for seminars like this in the future? And we will come back to that. The answer is yes. Stay tuned. We are going to have 2 more this spring, and I will provide information in the chat. Ahmed also asked, is sensitization of stainless steels in structural applications a big issue, especially when they are welded, and what resources are available on that?
This is generally, if you're welding 304, 316, and you don't use low carbon, I've certainly seen sensitization. I've been the metallurgist for the Arch for a while and did the 50-year evaluation. And I can tell you that those welds were, and of course that was before we had AODs. There was sensitization at the 5 welds that an act of Congress was needed for me to assess. Now, the environment was not severe enough for there to be visible corrosion beside the welds, but they had been sensitized. So it can happen. You really, and the guidance that I think that most metallurgists provide about when you really need low carbon has changed over the years. Based on my experience, I usually say if it's an 1/8 of an inch thick or greater, then you really should specify low carbon. There are older publications, earlier in my career, I used to say 1/4 of an inch, but then I saw examples, down to an 1/8 of an inch, where they managed to sensitize the stainless steel. So yes, it can certainly be an issue, which is why we do strongly encourage, because I can't use the R word, while consulting for the industry associations, but we very strongly encourage you to use low carbon 304 and 316 if you are welding them. And I always say down to, anything 1/8 of an inch in thickness or greater because of my own personal experience. And I don't know, Gary, maybe you've seen somebody manage to sensitize at something even thinner. But that's the bottom end that I've personally found.
Yeah, no, I agree with, for structural applications, that's a very good rule to follow.
Okay.
Okay, are there any more questions?
There are. There have been so many great questions. Thank you so much, everyone, for all of your engagement today. Next question is, for maximum corrosion resistance using 304L, what welding technique would you recommend?
Gary, I'm bouncing that to you since you're the welding expert on this call.
Well, I would say virtually any welding process except oxyacetylene. If you're using an L, the question was if you are using an L grade, was it?
Yeah, I think
Yes.
he said
Yes.
L.
Yeah, and then
Or
you can
sorry,
use.
they. I didn't know the name.
You can use any of the, gas metal arc, tungsten metal arc, laser, sub arc, any of those are suitable, and are used regularly and give good results. And of course, a flux core and almost every technique except for oxyacetylene welding.
Okay, thank you. Next question is, are martensitic stainless steels appropriate for building applications?
Well, I guess they could be including a 1010. Is the person that asked the question on the call still? And if they are, could they unmute so that I can better understand the question?
Catherine, one thing that might be clarifying is some folks are not in the Zoom meeting. Some folks are just on LinkedIn Live. And that was
okay.
one of the questions
right,
that came in through there. Yeah.
Okay. So we, if they are really talking about A1010, it is not included in AISC 370. There has not been enough structural research done, so it has not been included. That doesn't mean that it couldn't be in the future. That doesn't mean that it hasn't. I mean, it is being used for bridges. I mean, I tend to think of it as more of a dual phase rather than strictly a martensitic, but I'm assuming that was what the question was. So yeah, it would be. It's not going to appear in AISC 370, which is a specification for structural stainless steel, until there's more research, because there is a minimum level of research that's required. And it would be, wonderful to if stainless steel producers were to sponsor that research. But until we hit that minimum bar that's required in AISC or ASCE, it's not. But I do want to recognize, obviously there are bridges being built from it. It would depend on the application, whether something might undergo impact, how the temperatures, all sorts, a variety of, there might well be some limitations. It is less corrosion resistant too. So I'm not saying it can't be, but we need more data to include it in the specifications.
Okay. Um, I think there is one or two more questions. On the LinkedIn side, one is how do we correlate a higher PREN number to more resistance to, I believe you're meaning chloride stress corrosion cracking in the case of duplex stainless steels. You know, if you want me to repeat that.
I mean, rather than for a specialized form of corrosion, I would not use the PREN numbers. I would look at the data that is available, and some of which is in some of the Nickel Institute brochures, in particular, I think it's the high performance stainless steel brochure that contains, much of that data. I think there's also some in, I think, the duplex brochure as well. But I believe it was high performance stainless steels that had far more of that type of data, several tables, and a larger section. Gary, is that the right brochure that I'm remembering in the title?
Yeah, that's the most appropriate one, I would say, because it also has the austenitics and it has the duplex alloys in that one, so it compares the two. And of course, the structure of the material, which is not considered in the PREN number, it can be important. Yeah.
Right. Yeah. Yeah, I was trying to think if there was anything else that was better. I mean, that it summarizes data. Research has mainly been done by the stainless steel producers, if I remember correctly. So,
Yes.
And presented in in international forums. So it would be a good place to look to understand that difference and can do a comparison. Anything else?
I'm just seeing one more here. What is the future of HD stainless steels? It seems like they are underestimated. Not sure if that means high density stain. Sorry. It just says
HD?
HDSS. I'm not sure if that means.
I think
Yeah.
it might mean hyper duplex stainless steel.
Yeah.
Oh, okay.
Yes, and he was asking, what is the future? I'm hoping of hyper duplex stainless steels. It seems like they are underestimated.
You want me to answer that, Catherine?
Oh, sure. Go ahead.
The main limitation of hyper duplex stainless steels is a thickness limitation on them, because beyond a certain thickness you cannot weld it in good properties in the heat affected zone. Now there are couple different types of hyper duplex. So some of them you can do a little thicker than others, but they make excellent seamless tubes. You might be able to do sheet in them, but you'll never do, let's say, a 1/2 inch, 12 millimeter thick plate in it. That just won't happen. So that's the limitation on them. So they're not going to find as much usefulness as some of the other materials. But yeah, they do have their place.
Did you say that's the last of them, Carly? Or was there more?
I'm sorry, I'm just trying to go through them real quick. It's a little unwieldy. Let me see here. Oh, someone asked if you could please repeat what is the the standard for stainless steels in structural applications.
Okay, there are two. There is AISC 370. That is the specification for structural stainless steels. It's really for anything that is, well, a heavier section. If you're talking about a 1/4 inch in thickness or more, hot rolled product. There is a companion code of standard practice, which is AISC 313. That covers the erection and fabrication of stainless steel. So if you are working with the International Building Code, you definitely need both documents, because 313 was needed for 370 to be included in the building code. ASCE 8, and it's usually referenced ASCE/SEI 8, is for the cold formed stainless steel. Next month, the 2022 version will come out. It's been 20 years since an update was issued. So the cold formed standard now includes duplexes. It didn't used to. The austenitics have been updated and expanded, and it has the latest knowledge of structural design with cold formed stainless steels. Both of them, I should note, reference the AISC Design Guide 27, which is a book that provides more guidance on various aspects of specifying and using stainless steels. And it in turn has references to some of the other brochures that we've been talking about today.
Okay, I think we have answered just about everything here. The only thing is, there was a question by Mr. Kunj Gupta that I couldn't see earlier, but now I have relocated it. That was the person who asked, what if the water was sweet, which Kunj, I'm not sure if you're still watching. Correct me if I'm wrong in the chat, but I believe that means what if the water is fresh, and can common stainless steels be used in that case for long-term immersion?
By fresh, I am going to assume that it is not treated water, that it's natural water. There is a big difference between natural waters and treated waters. And there can be a lot of variables. Sometimes that natural water it can have microbes that could cause mech issues. It can have salt content. It can have could be acidic. There are a lot of variations, and there is a Nickel Institute brochure that covers, it does discuss what you have to consider as you're specifying stainless steel for different types of waters, and that I'm pretty sure includes natural water. And actually, there might be several brochures on that topic. That also not only cover fresh water that might be inland, but also, different levels of salinity content, as you have perhaps brackish water or seawater. I can't remember the names of the brochures off the top of my head, Gary. Do you remember?
No, there's several that cover that subject, and we're coming up with a new one which combines all of them, but it hasn't been released yet. So But it's one of those, if you have any sort of questions like that, we put on the Nickel Institute technical service inquiry line, which Carly had shown earlier, sorry, Catherine had shown earlier, and we'll answer it and give you the specific numbers of publications.
Yeah, I don't know if
Thank
my
you.
screen is still live.
Yep, I see it.
Oh, there
That one.
it is.
Okay, I think that
Yeah.
is all of the questions. If anyone wants to ask a
wonderful
question.
to have so many. Yeah, it's wonderful to still have so many people participating 30 minutes after we finish. That's obviously there were a lot of interest, and I hope we helped you.
Please join us for the next two that are coming up, which Carly will send out information on if she hasn't already. Oh yeah, there she has already in the chat. Yeah.
And if anyone has any follow-up questions, I've also dropped my email in the chat. Feel free to direct those my way. I can then forward them to Catherine and or Gary if need be. But any questions about continuing education credits, certification, future webinars, I'd be more than happy to answer those. And thank you so much. Again, those next two webinars that we're having, we have stainless steel for excuse me, this is a bit of a tongue twister. Stainless steel for sustainable design, which is going to be Tuesday, May 16th at 1 p.m. Eastern Daylight Time. And sunscreen and shade design with stainless steel, that is 2 weeks later, Tuesday, May 30th, also at 1 p.m. Eastern Daylight Time. These are going to be presented in the same format via both LinkedIn Live and Zoom for those seeking AIA credit. And you can stay tuned via LinkedIn or just shoot me an email for details about joining those webinars. Thank you so much.
Thanks, everyone.
Thank you, everyone.
Right, I'm going to close down the chat. Thank you again.